Welcome back to The Explainer. Today we're diving into topic 13, lateral earth pressure and the stability of retaining walls. If you've ever walked past a massive retaining wall, you've probably just taken its quiet strength for granted. But behind that concrete or stone face is a dynamic, high-stakes battle of soil mechanics. So let's jump right into this fascinating world and look at the invisible, yet absolutely immense forces of soil that civil engineers have to battle every single day. Here is our roadmap for this explainer. We're going to cover the hidden forces of Earth, the three states of pressure, water and surcharge complications, the Coulomb and Rankine theories, and finally, ensuring retaining wall stability. All right, let's kick things off with Section 1, the hidden forces of Earth. So the central conflict in geotechnical engineering really comes down to this. The Earth naturally wants to spread out, and our structures must hold it back. That push is what we call lateral earth pressure. And for those of us in the field, we know this isn't just some static number you pull from a chart. It's a highly variable force. It's dictated by the height of the backfilled soil and the very nature of the soil itself, heavily influenced by things like porosity, water content, and unit weight. But hey, before a wall even moves a millimeter, we have to talk about zero, specifically absolute zero lateral strain. We call this the at-rest condition. Just imagine an element of soil deep, deep underground. It deforms vertically under its own self-weight, sure, but its lateral strain is absolute zero. Why? Because it is completely prevented from deforming laterally by the infinite extent of the soil surrounding it. Basically, it's locked in place by adjacent restraints. Moving right along to Section 2, three states of pressure. Once a retaining structure actually begins to shift, that at-rest restraint totally vanishes. And there are three primary states of lateral pressure you need to keep in mind here. If the retaining wall yields and moves away from the soil expands slightly and the pressure drops to what we call the active state. On the flip side, if an external force actually pushes the wall into the backfill, compressing the soil, that pressure skyrockets to the passive state. So the crucial takeaway is that the at-rest pressure sits squarely in the middle between the extreme high of the passive state and the low of the active state. The S-curve brilliantly illustrates that whole dynamic. Notice just how dramatically the pressure shoots up into the passive state when a wall is pushed into the soil. But, and this is wild, if the wall yields outward by a tiny fraction, roughly 0.50% of its height, the soil hits the fully active state, dropping the pressure significantly. It takes remarkably little movement to trigger this shift.
Next up is Section 3, water and surcharge complications.
Because let's face it, in the real world, we are rarely dealing with perfectly dry, uniform soil. Environmental variables radically alter our baseline calculations. For instance, a submerged backfill changes the math entirely. You suddenly have to do buoyant unit weight calculations and add in hydrostatic pore water pressure. Alternatively, imagine an external uniform surcharge, like a whole highway resting on top of the backfill. That adds a constant, linear pressure all the way down the face of the wall, heavily compounding the active thrust.
Which brings us to Section 4, Coulomb and Rankine theories. To actually calculate all these complex forces, engineers rely on some heavily time-tested math. In geotechnical engineering, you are going to constantly hear two names. First, Rankine's theory. It's relatively simple and assumes a completely frictionless wall. Because it's so straightforward, it's pretty much the go-to for standard, everyday designs. Then you have Coulomb's theory, which is generally considered more rational and versatile. Actually, it can be pretty mathematically cumbersome, but it accounts for real-world factors like wall friction, the actual grit and friction between the rough back of the wall and the soil. It also accommodates tension zones near the surface of cohesive backfills, which makes it absolutely essential for those complex, high-stakes problems.
Looking at Coulomb's sliding wedge theory, which dates all the way back to the 18th century, by the way, he visualized a rupture plane where a wedge of soil acts as a single rigid body sliding downward. Pay attention to the active thrust, labeled PA. Not only does it act at exactly 1/3 of the wall's height from the base, but it's not perfectly horizontal. It actually makes an angle of friction, called delta, with the normal to the back face. That right there is wall friction in action.
Finally, we've arrived at Section 5, ensuring retaining wall stability. So how do engineers actually apply this math so these walls don't just collapse? Well, when designing a gravity-retaining wall, the structure relies heavily on its own massive weight. These structures, along with the retained backfill, form a highly indeterminate system. You literally can't figure them out through simple statics alone. Because they have to oppose tremendous horizontal loads, their scale has to be massive.
As a general rule of thumb to start the trial design, the base width of a gravity wall usually falls anywhere between 30% and 60% of the wall's total height. To put that into perspective, if you're building a 10-meter tall wall, the base buried underground might be up to 6 meters wide. Once those trial dimensions are set, the design has to survive the ultimate stability checklist. Every single gravity wall must pass 4 stringent tests. 1. The maximum downward pressure on the base absolutely cannot exceed the safe bearing capacity of the foundation soil beneath it. 2. Zero tension can develop anywhere on the wall, mainly because materials like concrete or masonry are frankly terrible at handling tension. 3. It needs an adequate factor of safety against sliding outwards. And 4. It must have an adequate factor of safety against overturning, basically making sure it won't topple forward like a felled tree. The total resistance just has to safely overpower that active thrust.
Now, to bridge the gap between pure textbook theory and applied construction, engineers rely heavily on empirical data from field experts. Take Carl Terzaghi, who is often called the father of soil mechanics. When you're using Coulomb's theory, you need to know that angle of wall friction. Terzaghi gives us a super practical rule of thumb. It usually ranges between 1/2 and 3/4 of the soil's internal friction angle, which is known as phi. And if you're out in the field and just lacking specific data, Terzaghi recommends just using 2/3 phi. It's exactly this kind of practical wisdom that makes real-world design possible.
So the next time you walk past a massive concrete retaining wall lining a highway or supporting a hillside, take a moment to look at it a little differently. It is not just a static piece of architecture. Ask yourself, is the earth behind it resting, or has that wall yielded that tiny fraction of a percent, and is the soil actively pushing back? The silent, invisible math of lateral earth pressure is happening all around us. Thank you for learning with The Explainer. Keep observing, keep questioning, and we'll catch you in the next one.